So thanks very much for the introduction, Sven, yesterday and today. And thanks for all the talks that have been given so far. I put my slides down there at that bit.ly location. Hopefully you can get them, and we should have some fun here. Okay, so how did I get here? Well, I grew up on the southwest side of Chicago, and I wanted to be a high school teacher. So I wanted to teach science in the Chicago high school system, and I attended the normal school in Chicago that trained most of the teachers. It was Chicago State University, and I took a lot of math and science courses as an undergraduate. I did pretty well. In my last year in college, everything really changed. So the chair of the physics department at Chicago State is a guy named Harvey Left, and he suggested I apply to Argonne's undergraduate research program. So this is a program that allows 50 undergraduates from around the country to come and to spend a semester working with a scientist. And the thing I didn't realize is that Harvey Left was a college roommate of Jim Poole, and Jim was the head of the applied math division at Argonne. So Harvey called Jim and said, this guy's going to apply, you might want to look at him. And I was selected. Jim pulled my application, and I spent my last semester at Chicago State with Argonne. And in particular, I spent it with Brian Smith. So I had no real formal training in computer science, and I had very little programming experience. And Brian was very generous in his time and helped quite a bit. He was leading the IcePack project, and I tried quickly to learn all about linear algebra and eigenvalue problems. And during the course of that semester, I made tremendous progress in my understanding of computers and what little linear algebra I gained. And I realized that computer science was really where the fun was, and I wanted to pursue that. So I applied to a number of places. I applied to University of Chicago and Illinois Institute of Technology to do a master's degree. And I was accepted at both places, but IIT offered me a graduate fellowship. So I went to IIT, worked on my master's, and while I was there at IIT, Argonne, Brian, said I should come and work one day at Argonne if I had time, and to continue working on IcePack. I was really sort of a gopher. I was helping with some of the testing that was going on, and I did that. So I worked one day a week at Argonne. When I finished, I got a master's degree. I wasn't sure I wanted to pursue a PhD, so I finished with that master's, and Jim Poole, with Brian's, I guess, advice, offered me a position at Argonne. So I joined the staff at Argonne with my master's degree and continued working on the IcePack project. And that was a wonderful thing. So there I am in what year is it? 1973. Ian mentioned that he hadn't seen me with a tie before, or maybe it was Sven. There I am with a tie. At that time, most of the people at Argonne wore ties to work. And so I wanted to fit in with a group, and there's my very fancy tie. You probably know the guy on the right there, Jim Wilkinson. Many may not know the guy on the left. I didn't. I was at Argonne. I was with the group, of course. We went to lunch at the Argonne cafeteria, a short walk from the math division building. And a group of us went there. And the first week I was there, I sat around a table, and around the table was Brian Smith and Jim Cody and James Linus and a few other people. This guy here on the left was there as well. He introduced himself as Wallace Givens. I hadn't known Wallace. I didn't know what a Givens transformation was. I wasn't impressed. I went back to my office and started reading more about linear algebra and recognized that, hey, this guy here just has this great approach for linear algebra. And I was stunned and shocked. We had many visitors at Argonne over the course of time. Jim was a frequent visitor. He spent a number of weeks at Argonne every summer, gave lectures, and it was very engaging. And I got to know Jim quite well during that period. We also had a lot of fun, a lot of parties. Cleve showed this picture yesterday. He actually had it reversed. So this is the right way around, Cleve. Next time you show it, you should flip it. That's the right way it should be done. And if Brian Ford is on, there's proof that Brian was actually at that soccer match or not soccer match, but at that match playing as well. We had fun.
You gave me a print. I thought the print was the other way around.
I think you flipped it. Anyway, here's Pete Stewart getting wet during one of our summer fun trips. There was always a lot of visitors, and there was always a lot of drinks to be had. There's a picture of me at the Tektronix 4081 that Cleve mentioned. And I looked at that picture yesterday, and when I blew up the picture, I got, this is the image that's there. So I'm writing MATLAB, so I don't know if you could see it. It says MATLAB version 072980. So this must be a Fortran version of MATLAB that we had running on the Tektronix machine. I've got a matrix, it's the LINPACK matrix in alpha numeric code. And then I'm using the matrix, and I'm computing the archon of the matrix. So the reciprocal condition number is 0.0356 for the LINPACK matrix, if you're at all interested. And the MATLAB version produced the number of flops it took to do that operation. That's a feature we wish we all had in MATLAB today. So that was a lot of fun. Danny, of course, was a good colleague and friend. He had the office next to mine at Argonne, and we did many things together. And as I said, this was a fun time. The cricket match. I think we had a baseball game the following summer. I don't think it was quite as successful as the cricket match was, but we always had fun in parties. This is taken at my home with Jim and Heather and David Young there in the background, George Murray, my wife, and Doris and her husband at the time, Doris Payas, is in that picture as well. Always a fun time. We always had fun at meetings with various colleagues and friends, and always enjoyed partaking in refreshments as much as we could on the off hours, and just having fun in general. So yes, it was a great time. IcePack was really a project to translate some of the algorithms that were in the Wilkinson Range handbook. It was the handbook had ALGOL programs. The IcePack was intended to do a faithful translation of the ALGOL into Fortran. ALGOL was organized by rows. The Fortran was faithful to that and organized its operation by rows. And that led to some issues in terms of performance, as we found out later on. NAG was a big influence at Argonne, and with respect to my activities as well. There was a close relationship with the numerical algorithms group. My first overseas trip was arranged to visit NAG. Brian Ford invited me, and I came talking with Jeremy and Steve Haig. Sven wasn't there at that time, but I did meet up with Jim Wilkinson at NPL, and Sven happened to be there that summer. So that was our first meeting with Sven. I had met Jim, of course, at Argonne. Wilkinson graciously took me out to the pub for fish and chips and mashy peas, and had a great time. During that trip, I stopped off at Harwell. I think that was my first visit to Harwell. Ian had been to Argonne, so I had met him. I'm not sure that John Reed was there, but I met up with him. I gave a talk, and this could have been the talk I gave. This is referenced as my first paper, and it was with Alan Hines. Alan was one of the systems people at Argonne, and it was about unrolling loops. And as you've heard, it's a simple operation, taking a loop and just unrolling it a bunch of times to increase the amount of pipelining and concurrency that might occur. Compilers do this routinely today. They didn't do it at that time. And as Nick mentioned, you get about a 15% improvement in the code. I wrote up an LA-Pack or a LINPACK working note. It's LINPACK working note number 3 about Fortran BLAS timing. And I went through and did this for all the BLAS operations which were being proposed at that time. I had coded them up using this unrolling technique and showed how great an improvement in performance. That didn't go unnoticed by Lawson, Hansen, Kincaid, and Crow. And when they came out with their version of the BLAS, they referenced my implementation, and the version, in fact, that's in the Tom's algorithm section uses my coding of that unrolling technique, which was novel for that time. But today it's quite common. So we had the level 1 BLAS. We had this package called IcePack, and we were in the process of developing LinPack, and LinPack was intended to use those level 1 BLAS, do vector operations, and be efficient on perhaps vector machines. So that's the picture you've seen quite a bit of. LinPack was a project, an NSF project with some DOE funding. It was with Argonne, the University of New Mexico, University of Maryland, and the University of California, San Diego, where Cleve, Pete, and Jim respectively worked. We worked independently, and we came together at Argonne during the summer. So we had 2 or 3 months during the summers where we brought all the codes together, looked at the progress, and tried to put together this uniform package for it. It was a great experience for me working on this, and we had a lot of fun in the way. You've seen the previous picture. You may not have seen this picture, however, of us that was subsequently taken, or this picture. And this is where I became this accidental benchmarker, as Eric has pointed out, looking at the appendix B. We benchmarked a bunch of machines, and that was that list. It's curious that I have this unit here. Unit is something about the time it takes to do basically a floating point add multiply. So a unit is doing an FMA instruction. So this is the time for doing that instruction, and my scribble here is converting that into the execution rate. So NCAR was 14 megaflops is the execution rate for that Cray 1, the fastest computer at the time, and it goes down from there. I was encouraged to pursue a PhD by many of the visitors who came to Argonne. Cleve said he would customize the degree for me at the University of New Mexico. They didn't have a degree in computer science, so I would have to do it in the math department, but they would make an applied math degree. That's a picture of me when I was working at Los Alamos. That's my student ID card from the University of New Mexico. I was detailed from Argonne to work at Los Alamos for a half a year. And during that time, I got to program the first Cray 1. Using the LinPack benchmark, I was running experiments on the Cray 1, and I found a bug in the hardware. We were getting the wrong results. That is, the residual was turning out to be very large. I had run the same program on other machines, and they was quite low. I looked at the assembly code that the Cray was generating, and it looked fine. I talked to the hardware engineers and said, I think you got a bug someplace in the hardware here. The Cray had been running for months at this time. Nobody had reported any problems. And with the benchmark, they were able to determine there was, in fact, a hardware bug, and they subsequently fixed the bug. You wonder how many results were computed with that bug getting inaccurate or mistaken results. I spent 2 semesters I spent 1 semester at working on my PhD, taking courses while at Los Alamos. And then I spent 2 semesters on campus at University of New Mexico as a research assistant working with Cleve on the LinPack project. Cleve was going to take a sabbatical in my 2nd semester on campus. So he went off and said I should finish my courses, take my exams, and then come out to Stanford. And that was really a great experience. So I went out to Sarah House with a group there. And this is a picture of some of the people there. It's quite an impressive list of people. Randy Levesque, Jim, of course. There's Gene, Bill Corin, Walter Gonder, Frank Luck, Eric Gross. The first guy sitting on the left, that's the Lloyd Trefethen version, not Nick Trefethen. He subsequently changed his name. Stephen Nash, Marcia Berger, Peter Bjorstad is there, and I think that's Stephen Leone. So yeah, it was a great time, a lot of people, a lot of fun being had along the way. Gene encouraged Eric and I to work together and to develop something to help serve software. So the idea was, Gene said, we've got all the software laying around from graduate students and people are wanting it, and we're losing the software because the students leave and they can't keep track of the software after that. Could you put together a system that would deliver software to people in a more usable way using the network at the time? So the network at the time was using email. There was we set up servers at Bell Labs and also at Argonne, and the idea was to send email to netlib and in the body of the message say send a particular routine from a specific package. And that worked quite well. It had some smarts in it, so if the message was too long, it would break things up. And that was the way that we started this netlib collection. It's still in use today. I just took a snapshot yesterday from netlib's usage, and it's quite impressive. 1.27 billion things have been served out of the netlib repository at Tennessee. There's a mirror sites at many other places. Of course, this technology has been superseded by using the internet and doing things that way. But it was one of the first distributions of publicly available open source software distributions. My interest in mixed precision actually came from a lecture that Jim Wilkinson gave. So Jim was at Argonne. He was talking about improving eigenvalues. And I was looking for a research topic. Cleve was there as well and says, maybe you could work out the details of what Jim just talked about. So that's really where my interest in this came about. So the idea was to compute an approximate eigenvalue, eigenvector pair in some precision, lower precision, and then selectively use higher precision to improve the accuracy of that lower precision computation. So you do the computation in low precision using n-cubed operations, and then selectively use n-squared operations in the higher precision for improving the solution. So that turned out to be my dissertation. We got a publication in SIAM numerical analysis. I extended that to singular values. There's an algorithm in TOMS that talk about that today. So why do you use mixed precision? Well, a number of people have already talked about this. It's less communication. It reduces memory traffic and network traffic. It reduces the memory footprint, does more flops per second, lower energy consumption, reduces the time to solution. On accelerated hardware, you can get better performance, and it has many numerical properties that seem to work quite well. I did a brief postdoc at IBM TJ Watson, where I got together with Fred Gustafson and Alan Karp, and we recognized that matrix multiply, we have these three loops for matrix multiply. If we hold the innermost operation fixed and vary the IJK references here, we get 6 different algorithms, and they have quite different properties in terms of how the matrix is referenced and what the performance might be. So the 6 are highlighted there. Some would work well in C, some would work well in Fortran, some you could accumulate the results in vector registers, and there was a myriad of things that you might benefit from that IJK representation. We extended that to Gaussian elimination and looked at a Saxby version, something that we called a Gaxby version, a generalized Saxby, which is really a matrix vector multiply, and a dot product. And out of that come the left and right looking versions of algorithms. And in that paper, we talked about matrix references called touches here. And we showed that the Gaxby version has half as many touches, so communication would be reduced and the performance would be better under a certain set of conditions. So that was a useful time spent. I went back to Argonne with my PhD. I had my union card and was able to engage in discussions. This is a group from 1986. And a number of number of very close colleagues, Rusty Lusk, Bob Veroff, who was I shared an apartment and later a house with, Hans Kopper, who today is the SIAM News editor-in-chief, Paul Messina, who was leading the group, George Waray, Danny Sorensen, of course, Jim Cody, James Linus, Wayne Cowell, Bert Garbo, and Brian Smith, who was my early friend and colleague. Doris Payas here, Doris Poole, she later became Judy Bumer, typed up many of the reports that we did and had and took care of our needs in that sense. We developed LINPACK, and now we're moving on, and we realized that vector operations weren't enough. Got together with Jeremy and Sven and Dick Hansen to talk about matrix vector operations, and a year later, Sven and Jeremy and Ian and I got together and put together the standards called the level 3 BLAWs. And these were done with community input. They weren't done in a vacuum. They were done engaging the community and coming up with ideas that could help push that forward. So with that, we occasionally went off and had our summers in Europe. We've spent a number of summers working in England, in particular in East Hagborn, working at Harwell, working with the people at NAG in Oxford, and had many enjoyable occasions and very festive time with them partying on. Back at Argonne, we had really, Paul Messina had managed to put together some LDRD money. LDRD money is the laboratory discretionary funds. He managed to convince the lab to give us funding to buy some equipment, plus some money that came from the government. We put together this menagerie of parallel machines, and this was an incredible time. We got together and purchased 11 different parallel processors. Some had shared memory, some had distributed memory, some worked on data flow, some did parallel bit operations. There was a very large instruction word architecture, and we used these machines and learned from them. It was a wonderful time. We had workshops, we had students come in. We felt that we were the center of the universe in terms of parallel processing. And that was our cartoon riff from the New Yorker magazine. Danny and I used those parallel machines. I remember being in a lecture by Beresford at Argonne, and Beresford went on about rank 1 changes to a symmetric, to a tridiagonal matrix, computing the eigenvalues and how the eigenvalues would interlace with that rank 1 change. I went off and talked to Danny about putting something together in parallel. We concocted an algorithm, and then we realized that Jan Koopman had done that very same algorithm as his PhD dissertation. We looked at his algorithm and recognized that there were some scaling issues there, and we did implementations on a parallel machine and recognized or noticed that there was this deflation that would take place when we computed eigenvectors, and that led to really a tremendous enhancement in the performance. So we wrote that up and published that in CISC. In that paper, we talked about extending it to banded matrices as well. So not just tridiagonal, but you could think about extending it to a banded set of matrices. In 1988, the three of us, that's Rusty Lusk and Danny and I, we became senior scientists at Argonne. From there, I had a discussion with Bob Ward and Mike Heath. They talked to me about a position they had at Oak Ridge and the University of Tennessee. And Alan George had this position before. Alan George was a distinguished scientist at the University of Tennessee in Oak Ridge. He had moved from Waterloo to Tennessee. He was there about a year and a half, and then he decided that he had to move back to Canada, back to Waterloo, and they were looking for someone to replace him. So they talked to me, they convinced me this was a great opportunity, and with my my feeling that I was ready to move on from just working at a government research facility and to take on a university. So I took up the bait and put together a group. The first person I hired was Ed Anderson. He was actually hired at Argonne and joined me at the University of Tennessee, and Susan Osterkoff or Blackford was the next person I hired. And from there, our group grew quite rapidly. We had friends. You see Sven there in the background spending some time with us. Another postdoc was there with us. So she came and did some work with us. We had various students. We had many parties as well. That's Richard Barrett. Nick was a frequent visitor, and I was stunned. I was surprised that he was coming by Tennessee so often until I recognized that something was going on with Nick and Fran, and then it became clear why he was such a frequent visitor to Tennessee. And we've had many visitors over time at the university and colleagues working together. So it's always been a great place for working together. You see Eric in the background here with a slightly different hairstyle than today. He was a postdoc with us at the university. Given the work that Charlie and Chris Bischoff had done with block householder transformations, Danny and Sven and I got together and concocted algorithms for reducing matrices that we wanted to compute eigenvalues for using those blocked transformations. So we had a paper which appeared, and in that paper, there were exposition of how to do this for various matrices, for various eigenvalue computations. And that graph on the right is what was an attempt to look at a data flow algorithm for doing this, which we eventually implemented. So based on that, being able to reduce things using these block transformations, it was a clear path to doing the next package, LA-Pack, which used these block transformations to achieve very cache-friendly algorithms. We got together a group of people, Jim Demmel, of course, and Bai, and you see Sven and Jeremy there, and also a previous graduate student in the center photograph. So we had our meetings occasionally at the University of Tennessee. That was a hike that we took that Bai talked about in the Smoky Mountains, and we just had a great time putting that all together. In 1993, Eric and Hans approached me about doing this benchmarking thing. So we had a list of Eric and Hans had a list of the fastest machines, and I had a benchmark, and it made sense to put that together in this list of the top 500. Horst Simon joined our group a few years later and got things going. Parallel computing was a big deal. There were many ways to do message passing. Al Geist and Vidi Sundram had a way to do it using something called PVM. Liz Jessup came to Oak Ridge as a householder fellow, and she brought along a friend, Bob Manchuk. Bob was looking for a position. He said he could do some programming, and he was hired to help rewrite that PVM code that Vidi and Al had done, and to extend that in a way to use it on a programming system called Schedule. Schedule was a graphical programming language that I concocted. It was started at Argonne with Danny's help, and we pushed it forward. PVM was done by 6 people in the mountains of Tennessee. It had gained some traction, but there was really a need for a broader base standard that engaged more people. We had many message passing standards at the time, and it was clear that we needed something bigger than just that. So myself and Ralph Hempel and Tony Hay and David Walker got together and put together this proposal for MPI, message passing interface. The draft report was from November. We gathered the community together. This was an incredible situation. 40 people who had experience with message passing got together, met every 6 weeks at an airport hotel outside of Dallas to work on putting together a standard. At the end of that period, after a year and a half, we had something called MPI. And Ken Kennedy was really instrumental in getting us kicked off with that project. I was part of a project called the Center for Research on Parallel Computing that Ken had at Rice, which led to many great things. So given that we have message passing, we're able to do distributed computing now. So we took on the job of writing Scala-Pack and changing the LA-Pack routines to do message passing. And from that came many of the packages that came since, Plasma, Magma, using Parsec to get things going, and finally ending up with Slate. So Slate is the current project that we have to do distributed memory, working on heterogeneous architectures. This slide gives you, in some sense, a 50-year history of the software development for linear algebra, at least the stuff that I've been involved in for dense matrix problems. It really encapsulates a lot of that work. But I've had the fortune to be involved in many community activities, many projects that have engaged the community, from the BLAS to MPI to the top 500 to, as David mentioned, the IESP project. We've had various collaborative books and various national reports that have been put together. So I've been really in the right place at the right time. But I've had a great group of friends and collaborators that have helped with all of that. And they really have been very instrumental in doing much of the work as well. And that's still going on today with our friends and our colleagues. But today's environment for high performance computing is highly parallel. It uses distributed computing. There's heterogeneous things going on. Simple loops are really too limiting to really extract performance. So we need to go to things like directed acyclic graphs to get things running correctly. Communication is critical for getting performance, as Jim and others have mentioned. Today, we can't just rely on operation counts to get a reflection of how much time it's going to take to do things. The amount of work really doesn't reflect the amount of time. It's based on communication and other things that have to go on. And we have these other things thrown in using mixed precision, as Nick pointed out in the previous talk, and how important it is to help with that. So today we're still having fun. ICL continues. We got a bunch of projects that are carrying on many of these things, and it's still a very active time. This benchmarking stuff is accidental in many ways, as Eric is pointing out in my career, and it really is one of my hobbies, I'll say, and something that I'll probably continue to do for a number of years. So this is my group at Tennessee. The last time we met, which was about 1.5 years ago,
How many
as
slides
a
have you
group.
got left, Jack?
Say again?
How many slides have you got left?
I've got about 2 more left.
Okay.
All right. So just to say that we've had 33 PhD graduates here. There have been 34 postdocs, 135 graduate students, and 168 staff members. But I really have to say thanks to these guys. These guys are the reason why it really happened. Brian, Jim, Gene, Ken, and of course, Cleve. Thank you. And of course, I would be remiss if I didn't talk about my family. This is my family here with my 7 grandchildren. And of course, it's all because of my wife that it could happen. So thank you all. It's been great. I'd be happy to answer any questions, but thanks for putting on the party, guys. It's been a lot of fun.
Well, thank you ever so much, Jack. That's terrific.